Welcome to Math 31. This is Lesson 6 in the Introduction to the Fundamental Theorem of Calculus. And it takes what we've been working with and it just goes a little bit further. So it integrates the antiderivative that we've been working with and then the area issue that we were covering in the most recent lesson. So to start with, if we were to consider a function y equal f at x, just like this, here's our curve, and we have within a specific interval, a to b, we consider that this is going to be continuous and non-negative in this domain from a to b. So the non-negative issue isn't really a big deal, but it does make things a little simpler for us right now. We're trying to make sense of this whole thing. Now, by looking at this graph, it may occur to you, or may not, that you could designate the area underneath the curve from a to b as a function in its own right. Let's call it a at x. So area as a function of x makes sense. Now, if you arbitrarily selected anywhere in here an x value somewhere between a and b, and that makes sense because it is the x-axis after all, and then you were to consider, according to what we were doing yesterday with the Riemann sums, if you drew in a little rectangle. Now, I picked it where the curve is coming down again, but it doesn't really make any difference. This increase of the rectangle that we have drawn, so keeping in mind that to get the area, as far as we know, the only way we can do it is to draw these little rectangles. And what you're doing then is creating this rectangle with a width of delta x. So therefore, if you increase the x value wherever you are in that interval by delta x, it probably makes sense to you that the y value will, I'm going to use the word increase, but if you're going down, it would be a negative increase, a decrease. Doesn't really matter. But it will be changing by delta y. So I'll put that in just to make it perfectly clear. So you go from y, your original y, and then it will increase or decrease or whatever by delta y. Now, keeping that in mind, if we were to consider two possibilities, the two possibilities that we looked at last section was the inscribed rectangle part. So we have between a and b a rectangle like this. So I've moved this one over just to make it clear for the sake of the discussion that the left endpoint is going to be on the circle. So it's inscribed like that. Now in a case like this, when we've drawn it in this fashion, and here's your delta x for the rectangle, might make sense to you that the area, because this point there is x comma y, because it's the left endpoint, the area of that particular rectangle would have a width of delta x, and then it would have a length or height of just plain y, because it is the left. The height or the length of that rectangle would be based on whatever the y coordinate is on that x value. And then, if we were to look at the other style, which is the circumscribed rectangle, it's a little bit off there, but I'll fudge it by putting it in there. This is still delta x for the width, but this new point, the x coordinate is x plus delta x. The y coordinate is then going to be y plus delta y. So really, the area of this rectangle, if we do this version of it, is going to, the width would still be delta x of the individual piece, but the y value, instead of being just y, is going to be y plus delta y, or change or in y. So those are the two distinct versions we've got. Now what's meaningful is that the real or actual area is between these two. And we could call the true area of the rectangle, let's say delta A, and is between the two methods. This is where we develop a formula for this that will lead us to a better method. So I'm going to get a little bit more space to work, and I'm going to set up an inequation to describe this. So this delta A that we're talking about is on one hand going to be less than or equal to the circumscribed method, which doesn't matter which order you write it, but would be y plus delta y multiplied by delta x. And it will be greater than or equal to the smaller version of it, which is y times delta x. Now, these inequalities are inclusive, meaning that depending on the size of it, it could, of the rectangle you're working with, it could approach 0. So I'm going to actually have that inclusive like that. And now I'm going to simplify this mathematically. Now we have a few choices. I'm going to divide everything by delta x. Now this isn't the sort of thing that may occur to you, but it will lead us to a simpler expression because they divide out on the left and the right endpoints or limits. The problem is the middle one, they do not. But this is what we'll end up getting. On the lower limit, y is less than or equal to delta A over delta x, which is less than or equal to y plus delta y. And in this case, the delta x cannot be equal to 0. And here we make the next sort of step. We note that as x, even though it's not going to be equal to 0, as x approaches 0, it gets smaller and smaller. It may occur to you then that, excuse me, this should be as delta x approaches 0, delta y, the change in y, is also going to approach 0. So the smaller the x change, the smaller the y change. So therefore, it tells us as x gets smaller and smaller that, well, delta y gets smaller and smaller. So therefore, y plus delta y is going to approach just plain y. And this has implications because if we go back to this formula, then it doesn't affect the left side of the expression, but it does affect the right because as x, delta x gets smaller, so let's make a note again, as x, delta x approaches 0, the upper limit then is going to approach y as well. So y plus delta y gets closer and closer to y. Now we've got a very confusing looking expression right there because the lower limit is y, the upper limit is y. The only possible way to explain that is that the only value for delta A, delta x that makes sense, it has to be equal to y. That's the only way you can be greater than the lower limit and smaller than the upper limit. So we sit here for a second or two, and and we don't go anywhere. But then consider that delta A delta x is the derivative of A with respect to x. That's by definition change in A with respect to change in x. And this is important because it means that according to what we have, the y function, which is the original graph, is the derivative of the area function. So therefore, just write that out here, the derivative of the area function is the y is, let's say, is y equal f at x. So if you're given the area function, by differentiating it, you'll get the original function that you're graphing. Now you're probably thinking out there, well, I'm not going to have the area function. Who has an area function? And that's right. So in fact, we want to think of this in the reverse way. So more importantly, we could say the antiderivative of y equal f at x is the area function. This is critical because it means that instead of having to do what we did before by drawing all those little rectangles and getting the Riemann sum for the area under a curve, all we have to do is take the antiderivative of the function and we get the area function, and it gives us a formula that we can use to get the area. So the implications of this are really vast. It matters a lot because now we can do that for every one of those questions. We don't need to do Riemann sums. All we have to do is anti-differentiate the given function, and then we can take that formula and use it to get the area. So let's go on to a next question related to this before we get too formal about the whole thing. This question is going to say or ask us to get an expression that represents the area under the curve of this quadratic between, let's say, general points x equal a and x equal b, and also above the x-axis. So here we have the curve itself, and we don't know where a and b are. It doesn't really matter. It could be arbitrary values there and there, say. And if you want to get the area between them and above the axis, so say from there to there, and we deal with below the x-axis soon, not a big deal. We have to set up an antiderivative, an integral. So we would get the antiderivative, or of x squared plus 3x dx. But the difference is, because it's between x equal a and x equal b, we set up at the upper limit there of b and the lower limit there of a. And this is what we call a definite integral. And the definition more formally is coming right up. So thinking back to a previous lesson or two, a couple lessons ago, we had indefinite integrals, which were just the antiderivative, or telling you to get the antiderivative in a polynomial form or in a function form. A definite integral refers to the area between the lower limit a and the upper limit b. So it's written the same way, except that you have those two endpoints given to you. Now, we don't want to solve this one, but we can express it like this. So, in more formal language, I'm using big F, and you'll often see little f. It ultimately doesn't matter. Boy, that is pretty big. So this is the definite integral. And it means that when you're taking the area from a to b, or you want the area from a to b, from the lower limit to the upper limit, all you do is you take the antiderivative, f at b, minus the antiderivative of the lower limit. So that's what that implies. You work out the area for b, you work out the area for a, and then you subtract it. It's really quite simple. And this is equal to, another way, if we think back to yesterday's or more recent work, this really means the limit as n gets larger and larger, increasing without bound, of the sigma I is equal to 1 to n, and then f xi times delta x. So that would be putting it in context of the Riemann sum. Now this is also given a few other little things we should note. Given that given a function y equal f at x, and also where f at x is greater than 0. So for now, we work with the idea that we're above the x-axis. Now, a couple other things. Like I mentioned before, I'm going to write it down now. The definite integral is a number. So because it represents the area from 2 points, it's going to be a number, a value. The indefinite integral is a function. So they're very closely related, because you always, for the definite integrals, you have to find out what the antiderivative is. So it really is dealing with an indefinite integral, but you have to get the number ultimately with it. Now the other thing is the integrals, in the context we're looking at them, refer to area, but they can also be used for lots of other applications. So basically everything that you did before in differentiating, you can do the reverse. But for now, the thing we're going to look at is concentrate on is area. So let's do a few questions on this before we go to the next big topic on this. Here you're asked to find the area between the function 4 minus x squared and the x-axis, which looks like this. So we're making it easy because the x-intercepts are going to be negative 2 and 2. So we don't have to deal with being below the x-axis. Now the way we would write this, we could say that the area from negative 2, the lower limit. Now if you didn't have this function in front of you, you would have to calculate the x-intercepts. But this is simple enough, I won't worry about it. The area from negative 2 to 2 is equal to the definite integral from negative 2, lower limit, to positive 2, upper limit, of the function 4 minus x squared. So the original function we're given, then dx, if we take the antiderivative of it, it gives us the area function. So that's what you want to get clear on. The antiderivative of the given function that you're graphing will give you an area function to calculate the area. So when we get here, we take the antiderivative of 4 minus x squared. So anti-differentiate (4 minus x squared). And what you end up getting is 4x minus, well, that would be x3, 1/3 x3 plus c. Now the way that we write this is like this: 4x, big old bracket, minus 1/3 x cubed plus c. And there's a couple ways. I'll show both, but right now this is the most common. At the end of the brackets, for those square brackets, you put the upper and lower limits like that. So that's telling any observer that you have taken the antiderivative of it, but now you're going to substitute those values in. And we subtract. According to what we saw in the definite interval, we get the area of the upper minus the area of the lower, and then that gives us our answer. The thing is, as well, the c. Normally, when we look for the c by getting initial conditions, and here we don't worry about it so much. We don't need to worry about it because when we subtract, the c's are going to cancel out. So I'll show that for this first step, and then I'll never worry about it again. So this is going to be 4 times x is 2 minus 1/3 times 2 cubed plus c. So there's our upper limit substitution. minus 4 times negative 2 minus 1 over 3 times negative 2 cubed plus c. And then we subtract. So the c's cancel. So I'll do this one slowly. Later on we'll start just driving it through the calculator. But 2 cubed is 8. I'm going to keep the c's up for now, but not for much longer. And then this is negative 8. Now plus 8 over 3. So watch your signs. Negative 2 cubed is negative 8 times negative 1/3 is positive plus c. So we end up getting 8 minus 8 over 3 plus c plus 8 minus 8 over 3. And if you get all of those together with a common denominator, you will get 16. And then minus the two 8 over 3's. I believe that gives you 32 over 3. So that's what this whole thing is equal to. So the area is 32 over 3. So let's do, we did that. Let's take a look at one more and then note the fundamental theorem of calculus, which kind of summarizes this. And then we're out of here. Oops. There we go. There's our full graph. That's better. So find the area between the curve, another quadratic. This time between x is 0 and x is equal to 2. Now there's nothing really remarkable happening with this one. Again, we're above the x-axis. Now this is a temporary thing. Eventually we do have to venture below. But for now, this is good enough. And I'm going to do this one, the same method. And then I'm going to introduce something that might be helpful. The area between 0 and 2 is equal to the definite integral from 0 to 2 of the function 6x squared plus 12x dx. So reminder again, when you anti-differentiate the given function, you're getting the area function. So this becomes, when we anti-differentiate this, it'll be x to the 3, and then 6 divided by 3 is 2. I think that was originally supposed to be a negative, but oh well. Keep it the way we have it. So 2x cubed plus x squared, 12 divided by 2 is 6. And I'm not going to, x2, I'm not going to put the c's in, which is typical for these, from 0 to 2. And now we just substitute in. So we get 2 times 2 cubed plus 6 times 2 squared minus substituting the 0 in, so 2 times 0 cubed plus 6 times 0 squared. Now you can use your calculator or not. It's not that complicated of a one. This becomes 16 plus 2 squared is 4. 4 times 6 is 24. Minus, and then this is actually going to be 0. So that's going to be equal to 40 square units. Now the thing that I will show you with this question that might make your life a little bit easier is you can also use your calculator for these. So on the calculator, it won't help you too much on exams or anything, but you can certainly use it for checking your work. We enter in the function y1, the original function, 6x squared plus 12x. And you've got it graphed. It's not a big deal with that. It should be similar to the graph that we just saw. Scale might be a little bit different. And make sure your window settings are, satisfactory for you. Then, if you go into the Calculate menu, so second function, trace, so calculate, amazingly, number 7 gives you a definite integral key. So number 7 is f at x dx. So this allows you to calculate definite integrals. So press number 7. They're going to ask for a lower limit. And for our purposes, the lower limit is 0. So x is equal to 0. Press enter. And then they're going to ask for an upper limit. And the upper limit is going to be 2 according to this question. So 2, and then enter. And then it'll work out an answer. It actually will shade it in for you as well. And they tell you that the integral is equal to 40, which is what we got. So that's how these questions go. Now very quickly I'm going to show you the fundamental theorem of calculus, and then that'll be it for this part. I will do more questions in the next video clip. So the fundamental theorem of calculus really is just restating what we just had. Given this function, or this integral, f at x, or given, y is equal to f at x, so we have an original function like this. It's just equal to, as we saw with the definite integral, f at b minus f at a, under certain conditions. If f is continuous in that interval from a to b, and of course if f is the antiderivative of big F. So sometimes you'll see the f's being reversed, not a big deal. But that's the idea with it. You take the antiderivative of the given function, and then you are getting a function that represents the area. And if you have an upper and lower limit, that is a definite integral, then you're able to get the area between the two. So it rivals the original slope of a tangent line in terms of significance. So that's why these are referred to as sort of the two main issues with calculus. And now we've sort of got them taken care of. So the rest of this lesson, I'm just going to go through the remaining problems, just playing around with definite integrals and showing a few things. Thank you for your time.